Okay, we ended with Cesar's nuclear reactor, which used deuterium as the moderator for a nuclear reaction. Werner von Heisenberg is a Nobel laureate. He discovered quantum mechanics. His main thing we talk about is the uncertainty principle. He was also Germany's lead man on the nuclear bomb. So, he is quoted with saying, "When the ends are deemed to be improbably achievable or irrelevant, the means become the most important consideration." Many people question why he stayed in Germany to work on it. He felt that it was a challenge, the atomic project. He really didn't think it was quite possible. He is noted for working on various works with uranium fission. His work actually determined where Germany was going to go attack looking for uranium. He did feel that graphite was more attainable. A German chemist, Walther Bohl's team, feared to absorb the neutrons too easily. The other moderator that can be used for nuclear reactions is heavy water. There was a product company in Norway, the Norsk Hydro, which is 150 miles west of Oslo. The Norwegians were not very cooperative. They questioned why Germany needs so much heavy water, so they actually sent that water to France. Jolie Curie, which was married to Curie's daughter, identified that heavy water could be used as a moderator and was a better moderator than graphite. And so Werner Heisenberg's uncertainty principle is one of our guideposts for quantum theory. So I've talked before that the classical model starts falling apart during this time period because they're doing experiments and it's not working. We talked about Bohr's model only worked on hydrogen, and the rest of that story is that the hydrogen only has one proton and zero neutrons until you get to its isotopes. All the other elements already have neutrons and protons put together, and that's why Bohr's model didn't work for them. We also talked about that uranium, Hahn expected it to decay to radon because radon is the stable element, and it actually decayed all the way to barium. So there's things happening that can't be explained by our classical physics. So in the uncertainty principle, Heisenberg tells us that it's impossible to know both things. You can either know where an electron is at or its velocity, aka how fast it's going. But you can't know both. You got to choose which one you're going to know. What happens in quantum model is we start getting more of a mathematical relationship going on with electrons. So instead of just drawing circles and saying they're like the solar system, we start applying math to it. Okay? Erwin Schrödinger. He took the Bohr model one step further, and he used mathematical equations to explain the probability of finding electrons in a certain area. And yesterday I talked about, or earlier I talked about Planck, and the Planck's definition of quantum theory is that you have packets of energy. Yes, that's part of the problem, and that's reason why Bunsen and Kirchhoff are so important, because they pointed out that every element has a fingerprint, and underneath classical theory, the light being emitted by those electrons moving from place to place should actually be a continuous spectrum, and it's not. We get packets of energy. That's those bands. So Schrödinger takes Bohr's idea and says, okay, there should be a mathematical equation to explain the probability of finding these electrons in these vicinities. So quantum theory is based highly on mathematical computations. And so he gives us the idea of some energy levels. Now, the other thing that Schrödinger is noted for, and I'm just going to take a side note here, is his cat. And the idea is that you have a radioactive material. You do not know at what point that radioactive material is. So when you take radioactive material, not all the atoms are at the same spot at the same time. Okay? Some are partially decayed, some are just starting to decay. And so he says you put that in the box, and you have this cat in the box, and you do not know what state those atoms are in, so therefore you don't know if that cat is alive or dead. So the cat exists in both states, alive and dead, because you don't know what state the atoms are in. Schrodinger's cat. But here's his model of the quantum theory. We start getting these sub-levels. So we had those energy levels by Bohr with a 1 and a 2 and a 3 and a 4, and that refers to your rows. But within that, we're going to see that these rows all of a sudden start taking on shapes because that's the probability of finding electrons. And now the periodic table is going to all come together, and it's all going to make sense. Completely logical what's going on. Schrodinger. Paul Dirac. So Paul Dirac is a very interesting person. They called him an Einstein of his friends. He worked with the idea of antimatter and fermions, and he added to the atomic theory with Schrodinger. Schrodinger and him will both earn a Nobel Prize together. Antimatter is material that's composed of antiparticles, which have the same mass as particles of ordinary matter, but opposite charges, as well as other particle properties such as leptons and baron numbers. Collisions between particles and antiparticles lead to the annihilation of both, giving rise to variable proportions of intense photons, which are gamma rays, neutrinos, and less massive particle-antiparticle pairs. The total consequence of annihilation is a release of energy available for work, proportional to the total matter and the antimatter mass, in accordance with the mass-energy equivalence equation E equals mc squared. So again, we go back to Einstein's theory. So here's what we're looking at. So you have matter on the left side, which is a hydrogen, and then we have the antihydrogen. Okay, so a good question is, well, what are we going to use this for? Well, we're actually doing current research on this in America, and I will talk about that later. But to give you an idea, we did discover the positron. It was discovered by Carl D. Anderson, and a lot of this research involves cosmic rays because we've noticed that some things happen with cosmic rays that we can't explain. And they're high-energy particles that come from space, and they shower our atmosphere with it. And they've tracked these cosmic rays to try to find out what's going on with them as they pass certain points. They've also looked into how far down into the ground they also go for just for more observation to try to understand what's going on. They behave like electrons. They have the same mass electrons, but they have a positive charge. So they finally concluded that these were positrons, and he won a Nobel Prize for discovery in 1936. Louis de Broglie. I took this quote straight off of Wikipedia because it's the best way of explaining it. So Louis de Broglie says, all matter can exhibit wave-like behavior. For example, a beam of electrons can be diffracted just like a beam of light or wave or a water wave. Matter waves are a central part of the theory of quantum mechanics, being an example of wave-particle duality. What happens with chemistry and physics during this time is that we had this wave-particle duality battle going out between the two. And they're having a hard time explaining what's going on because by classical it's not supposed to be doing this, but on the quantum level it is. So de Broglie takes his idea of lights and waves and he applies them forward onto the quantum model. And so the idea is that your electrons, we've already talked about having a probability of fitting somewhere, but your electrons are moving like waves through the orbitals.